Hello everybody, the iLord Root here, and today we're going to talk a little bit about Boolean logic. So what is Boolean logic? Well, logic itself is the study of math concerned with truth and falsehoods. So Boolean logic is a study under this branch. It deals with the two possible values, true and false, and so it makes it something called discrete. And in Boolean logic, there's no concept of, for instance, that something may be partially true or that something is kind of false. And there are systems that deal with this. Boolean logic isn't one of them. And it's also in algebra. You can set up logical equations and you can actually solve for unknown logical quantities doing this. So who should be studying Boolean logic? And of course, programmers, mathematicians, and electrical engineers at some point all study Boolean logic. And it's also useful for philosophers and public speakers. But it's actually relevant to gaming nowadays because games like Minecraft or Little Big Planet 2 add in functionality to utilize Boolean logic in order to create complex creations. And you can express all possibilities in a logical assertion that you might make using Boolean logic, using something called a truth table. And so the idea is that if you have n logical variables, that you have 2 raised n entries in your truth table, as seen here. Now there is something that I came up with that I thought might kind of put the utility of this into context. Imagine the problem of trying to get into a bar. Now there are at least 2 things I can think of that might affect your entry when you're trying to gain access to a bar. And if you're in the United States, the first is almost immediately obvious, that you have to be at least 21. And also in some bars, there's a policy set forth to where the bouncer determines whether or not you get in as well. And so we could split this problem up into 2 parts. We can talk about the predicate or the antecedent, which are the criteria that are required for me to get into the bar, and then there's the consequent, which is the actual ability to get into the bar itself. And in order to play around with this idea, I'd like to go ahead and introduce this idea of basic logical operators. The simplest of these operators is something called negation. And in negation, what you're basically saying is if you have some premise A, then the negation of A is only true when A is false. So if we were to use this to determine whether or not we get into a bar, let's say for instance that I am not at least 21 is what's required for me to get into the bar, then being greater than or equal to 21 would mean that I wouldn't get into the bar at all. And then you have something called conjunction. And conjunction is basically when you take 2 premises, and only when both of them are true is the conjunction true. And so let's say for instance that in order for me to get into the bar that I have to be at least 21 and that the bouncer has to favor me as well. Well, of course, one of them isn't sufficient for getting into the bar. Both of them have to be true if I'm going to actually gain entry into the bar. And there's also the disjunction, or the OR operator. And with that, either one of those assessments could be true. So it's worth pointing out that this isn't usually what we mean by OR in colloquial speech. We usually mean one or the other, but not both. But with the OR, we simply mean one of them has to be true. And so, for instance, if I were to say I'm at least 21 or I'm favored by the bouncer, then either one of those is sufficient to get in, and the combination of them is also sufficient to get in. Taking these operators, we can actually come up with so-called derived operators that are a combination of these, and we can come up with some fairly useful ones For instance, something to replace our colloquial version of OR, which we call exclusive disjunction. And so if I were to say A XOR B, then either A and B can be true, but if both of them are true, then it's false. And the way you can alternately state this is A and not B, or not A and B. So if we were to use this as a policy to get into the bar, then I can be at least 21, or I can be favored by the bouncer. But if both are true, then I can't get in. And there's also material implication. And so you can imagine material implication being like this if-then thing. And in this case we have two things. We have the predicate and the consequent. You remember this from the beginning of the video? That basically makes our problem an implication problem. And those are referred to as P and Q respectively. And so what's going to happen is that the predicate A, it doesn't matter if it's true or not. All that matters is if B is true. And so what we can say here basically is that if we say that the validity of the statement I'm at least 21 implies that I'm favored by the bouncer lets me in, then the only thing that won't let me in is me being 21 and the bouncer not favoring me. And this can be alternately stated as not A or B. So we have this thing called DeMorgan's law, and what DeMorgan's law is used for is taking a compound condition like A or B and A and B, and it allows us to actually go through and count its or create its inverse. And so what we do here is we negate the operands and then we switch the operator. So for instance, the negation of A or B, here read A or B quantity bar is not A and not B, and not and is similarly not A or not B. And so what about some of our more complex operators? Well, because they have an alternate form that stayed in terms of the basic operators, we can use DeMorgan's law on those as well and derive the inverse. And here we do that with the XOR, which you might remember is A and not B, or not A and B. And if we do the math by using DeMorgan's law, we end up with not A or B and A or not B, as seen here. So there are just a couple of things I wanted to mention that aren't necessarily something I would put into one category, but are useful to know about nonetheless. And the first of these things is the paradox. And so a paradox is something where the result is always false no matter what the inputs are. And an example of this is A and not A. If you wanted to come up with a similar sentence in English, that would be something to the effect of everything I say is a lie. Well, there's no way that can be true, right? And so everything I say is a lie is a paradox. And you have its complement, the tautology. And a tautology is always true, and in fact, you could say that the conditions here are independent of the outcome, meaning that no combination of these will result in a false value. You can just replace it with true. So an example of this in Boolean logic is A or not A, and an example in English using the similar logic is I'm either a robot or I'm not a robot. And so you can see here that there's no way for that to be false, so it's a tautology. And we have this attribute of implications called contraposition, and contraposition is the study of implications, more or less. And so if we call our original implication the identity, then there are a few things we can say about it. Let's take the claim, for instance, you are a politician, therefore you are a scumbag. Well, the predicate is said to be sufficient for Q, that it's enough for you to be a politician, for instance, to be a scumbag. And the consequent is also said to be necessary for the predicate, meaning in this case that in order to be a politician you must also be a scumbag. So what ways can we manipulate that? Well, we can take the inverse and say not P implies not Q. And in English this should be something similar to you are not a politician, therefore you are not a scumbag. Notice here that the inverse isn't necessarily equivalent to the identity. And additionally, we have this thing called the converse, where we switch the order by saying that the consequent implies the predicate. And again, we have the situation where it's not equivalent to the identity. So, for instance, saying you're a scumbag, therefore you're a politician, isn't necessarily true. However, one formulation, the contrapositive, is logically equivalent, and it's combining the converse and the inverse in that case. And so it must be true that you are not a scumbag, therefore you are not a politician, if its identity is true. And you can derive this by actually using DeMorgan's law on the converse. Finally, we have something called a contradiction with an implication. And a contradiction is basically whenever the predicate is true, but the consequent isn't. And if you remember from our truth table there, that's false. So this basically makes the implication invalid. Finally, before we end this video, I wanted to alert you to the fact that there are multiple notations depending on your field for this. I've used the engineering notation, and in mathematics there's a different notation as well. If you're a programmer, you might deal with a different notation just from the fact that not all these symbols are available on your keyboard. So if you look at the engineering notation, you'll notice that a lot of these are similar to arithmetic operators, and that is because the engineers interpret these statements as being similar to their arithmetic counterparts. The mathematicians, on the other hand, tend to associate them with set theory. So here you have A and B being analogous to the set intersection, and you have A or B being analogous to the set union. And so that's all I wanted to say on that. I hope you enjoyed this video, and until next time.